Hello and welcome to Chapter 4B. We will continue our lecture on mortality as a measure, and we will discuss common problems that arise from mortality data. We will introduce you to age adjustment and how and when it is being used, and how not age-related rates can be misleading. Most of our information about deaths come from death certificates. The International Classification of Diseases, or ICD, is used to code deaths according to the underlying cause of death. The underlying cause of death is defined as the disease or injury which initiated the train or morbid events leading directly or indirectly to death, or the circumstances of the accident which produced a fatal injury. Thus, the underlying cause of death excludes information pertaining to the immediate cause of death, which means the total contribution of a given cause of death may not be reflected in the mortality data as it is reported. The ICD is now in its 10th edition, and you need to know that coding categories change from one revision to the next. Here's a death certificate for the state of Maryland. You can see a more detailed picture, inside your text. I believe it's on page 74. And again, here you can see how the deaths are coded according to the underlying cause of death. Notice that the true cause of death is shown on line C. Okay, so right here, chronic ischemic heart disease. But the cause of death is listed as a rupture of myocardium, okay? So this is the cause of death according to this death certificate, okay? So if this was a different version of the ICD, probably it would not be recorded as that. Maybe the chronic ischemic heart disease actually would be the immediate cause of death in the previous version. So when we calculate mortality rates for a specific disease or a specific age group, several issues may arise. The most common problems epidemiologists encounter are errors in diagnosis, especially if the individual suffered by more than one condition, or an underlying condition went undiagnosed. Human error recording age, any changes in the ICD codes, or how we classify diseases. Most common denominator issues have to do with the fact that obtaining accurate data for a lot of people is very difficult and bound to errors. Anything from accurately counting everyone to classifying persons based on geographic and demographic characteristics while taking into consideration that people move makes it a very complex task. This graph shows how mortality rates can change over time. Without knowing what changes took place between 1930s and 1960s, one would conclude that diabetes rate dropped significantly for both men and women around 1949. So you can see the immediate drop right here. News to celebrate, right? Not exactly. What happened in 1949 was the ICD codes got revised and moved from the 7th edition to the 8th. According to the 7th edition, any death that mentioned diabetes anywhere would be classified as a diabetes death. When the 8th edition came out, that rule changed, and only deaths with the underlying cause as diabetes would be classified as diabetes, which meant if diabetes was mentioned elsewhere, it did not count. Thus, the observed decline was artificial and not actual. So you can see right here is where the ICD changed. In 1993, a new definition of acquired immunodeficiency syndrome, HIV/AIDS, was introduced, and as it's shown on the figure, it resulted in a rapid rise in a number of reported cases. Again, this was artificially done, and it was not a true figure capturing what was happening in the society. We talked about incidence data and how incidence rates is a measure of risk. You may wonder why we need to look at mortality rates for assessing risk. Well, depending on the type of disease, mortality rates can provide a more complete picture of what is going on. First of all, mortality data is much easier to obtain than incidence data. When a disease is not severe and not fatal, mortality rates will not depict any risk. But if the disease is extremely fatal, meaning from the moment of diagnosis to actual death, the time is very short, the mortality can indeed be used instead of the incidence data. A mortality rate is a good reflection of incidence rate under only two conditions, and you should know those. One, the case fatality rate is high. So, for example, untreated rabies, if you're not treated rabies, you will die very soon. And two, the duration of disease is short. Survival time is minimum, is limited from the moment of diagnosis to actual death. Now we're going to talk about age adjustment of rates. An important function of mortality data is to be able to compare two or more populations, or one population in different periods of time. Populations may differ in regard to many characteristics, such as age distribution. Thus, comparison can be flawed if we do not effectively hold constant such characteristics. We cannot take age out of the equation, but we can control it by adjusting. Here's an interesting comparison. We have the population pyramid for both Italy, an industrialized nation, and India, a developing nation. What do you see? So you can see that the two pyramids differ greatly, okay? In developing nations, the pyramid still looks like a pyramid. So you can see that in India, it looks like a true pyramid, meaning you have a lot of young people at the base, and as you grow older, due to lack of resources and adequate care of people, die earlier. In Italy, on the other side, and other developed countries, the pyramid started to invert, meaning people have less kids, so that's why the pyramid has kind of a narrow base, live longer, and die at a much older age than they do in the developing nations. You can imagine that has financial consequences, since caring for older people costs a lot of money. And once they move to retirement, they no longer contribute to the economy. Okay, so you can clearly see that the two pyramids look very different. Now, I want you to keep this in mind as we move forward and discuss a specific problem about age adjustment. All right, so the idea behind age adjustment is to make two populations comparable by applying the same age distribution to each population. We saw in the pyramids that in the previous slide that they looked very differently. The age distribution between the two countries were very different. So essentially, we cannot compare two things that are not similar. There are two ways of adjusting for age, direct and indirect. Here are the steps for direct age adjustment. Remember that with age adjustment, we are trying to change the age structure of the population. In direct age adjustment, we use a standard population to eliminate the effects of any difference in age between two or more groups. A table is always helpful to keep us organized and avoid errors. We start by calculating the death rates for each age group. We then select a standard population that is appropriate. For your homework, I will give you the standard population. We multiply the standard population to our previously calculated death rates to obtain the new expected death rates for each group. We sum the expected deaths and we divide with the total standard population to get the new age-adjusted mortality rate. So I know it looks like a lot. Don't get overwhelmed. Let's go ahead and do an example. Based on the crude mortality rates, it seems that in this example, the US has a higher death rate than India. How is that possible for a developing country to have less deaths than the US? We suppose they have better care here and people live much longer. So let's see what's going on. So now what we have in this slide is we start breaking up the age distribution. So prior to in the previous slide, let me go back. You can see that this is the overall death rate, okay, for India and the US. In this slide, we're actually breaking it up per age group. So we have less than 30, The population is going to be 600,000, number of deaths 60, okay? For the US, the population for less than 30 is 300,000, and the number of deaths is 30. 30 to 59, 250, number of deaths 396. In the US, we have 400,000 population here, and then 400 number of deaths. We can really see a huge difference when we go to the 60 plus age category. So here we have a population of 50,000 only in India with 406 deaths, where in the US we have 200,000 population with 700 deaths. Now, since we do have those numbers, that means we can actually calculate a death rate for each age group, right? So hopefully you remember how to calculate that. So you're going to take your number of deaths, right? So number of deaths for each age group, and you're going to divide it with the population of that group, and then you're going to multiply it with your base. So right here it says death rate per 100,000. So the 100,000 is going to be your base. So in this case, you have 60 divided by 600,000, okay? And multiplied by 100,000, that will give you 10. Okay, so you will do this for every single down. So for this one here, for the 30 to 59 category, you will get the 396. You're going to divide that with 250,000, and then you multiply with your base. And the death rate for that particular age category now is 158 people per 100,000. Okay, so you have 158 deaths rather per 100,000. You would do this for the 60 plus, and then you would do the same thing for the United States. Now we'll go ahead and apply the standard population in order to eliminate the age distribution differences. As you can see, under the standard population column, right here, I will give you those numbers. So this is not something that you will calculate, okay? I will provide you with a standard population. To calculate the new expected number of deaths, right, we will multiply the standard population to the age-specific death rates that we just calculated in the previous slide, okay? So you will need to transfer those numbers over, make a new column, okay? And then you're going to take those death rates and you're going to multiply them with the standard population. Now remember, it is a rate. So you're not multiplying 10 with 900,000. It's 10 per 100,000 multiplied by 900,000, okay? So make sure you do the math right. Likewise, here is 158 per 100,000 multiplied with 650, and that's how you're going to get the expected number of deaths, okay? So if you do those calculations that I just said, you're going to get 90 number of deaths expected for India for this age group, 1,027 for the 30 to 59, 2,030 for the 60 plus, okay? And then you would sum up, okay, all the number of expected deaths. You would do the same thing for the United States, and now you are ready to calculate the adjusted death rate for either country, okay? And of course, this is your total standard population. This is the new adjusted death rate. So the way you do it is you take your total number of expected deaths that you calculated in the previous, and you will divide that with your total standard population, and you will multiply that with your base, and then you're going to get the new age adjusted death rate. So here you have 175 for India and 90 now for the United States. Look how different that looks. So in the crude, it was the opposite. It seemed that the US had a much higher death rate than India. Once we age adjusted and we took into consideration the differences in age distribution between the two countries, we start to get a different picture, right? And the picture that we're getting is that actually the United States has a much lower death rate, okay, than India. And the reason is because, let me go back, just you can see from the age distribution here, you can see that India, for example, has a lot of young people dying, people in their 30s to 50s, where in the United States, that number is much smaller. Likewise, okay, if we kind of like adjust and make the plane even for the two countries, look how many people in the 60 plus category die in India and how many they die in the US. So essentially what this is telling you is that in the US, people die of old age, which is a good thing. That's what we want. We want people to die from old age, and we do not want them to die from disease or lack of care. And in India, on the other side, you can see that the fact that so many people die this young, that means that they don't have a good quality healthcare system. Okay, so people don't reach an old age, and the ones that they do, probably they will actually have larger number of groups dying than in the United States, because now supposedly the age population is equal and we can compare them. Adjusting does not have to be only for age. We can adjust similarly for sex, ethnicity, and so on. Keep in mind that age adjusting, or any kind of adjusting, is hypothetical because it involves applying actual age-specific rates to a hypothetical standard population. They do not reflect the true mortality of a real population because the numerical value of an age-adjusted death rate depends on the standard population used. Selection of such a population is somewhat subjective because there's no correct standard population, but it is generally accepted that the standard population should be pretty close to the real population being compared. As age distribution change over time due to advancements in medicine, standard populations need to change as well to capture those differences. In the US, we update our standard population in 1999 to reflect the growing segment of older adults. Again, here's a visual of those changes made to the US standard population. The gray line, this one right here, the gray line, not the black one, shows the 1940 standard, and the dark blue, it kind of looks like black probably now on your screen, okay, shows the 2000 standard. The US is still a young country, and we slowly start to see the inverting pyramid effects as more baby boomers reach retirement age, and they're expected to live a lot longer than the previous cohort. And finally, we can see that by changing the standard population, we are also going to see a change of the chronic disease rates. Greater numbers of older adults translate to increased rates of the most common chronic diseases, such as cardiovascular disease and cancer. So you can see here an increase, right, for heart disease. It went much higher. Okay, so this is the 1940 standard, and this is the 2000 standard. So by changing the standard population and taking into consideration that now we have a much greater segment of older people, you can see now that when we calculate those rates, they actually seem to almost double. Okay, so this has to do mostly with the age distribution and not necessarily that more Americans actually suffering from heart disease. So this is it. Hopefully you found this lecture interesting. Let me know if you have any questions. Bye-bye.